everyone is okay. This is our video number 22. And in this video, we're going to start with a new chapter, and that chapter is nuclear physics, right? So let's start with the nuclear physics, right? What exactly is nuclear physics and how does it work, right? So let's start with this. The question is, when you say nuclear physics, right? What do you mean by that? That's what the point is. When you actually say nuclear physics, it means something related to nucleus, right? When you say something related to nucleus, what exactly it is? Now, there are a few things which we need to actually discuss here. And what exactly are these? So, chapter is nuclear physics. Now, first of all, nuclear physics. In this chapter, what we are going to study, in this chapter, we will see that how does an element actually is there. I mean, how does it look like? There are different models came in. And first of all, the most important part is what is the smallest building block of, you can say, uh, any element. So it was for a very long period of time, the scientists saying the smallest building block, the smallest entity that belongs to any particular some sense, any particular element is basically an atom. And an atom is something that cannot be further broken down into any further, right? But as the time progresses, we found out some further subatomic elements like electrons, protons, and then definitely neutrons. Right? There are further elements we have discovered till now, but we are just talking about these three basic entities, right? Now, question arises how they are actually placed within the atom. For that, there are different atomic models which are being proposed. Different models. But definitely, they are not in our course. In our course, we will start with our Rutherford alpha scattering say a model. Now, what actually is happening in this? This is very interesting. Actually, what happened? Let's suppose what they did actually. It's a gold foil experiment. In this experiment, what actually happened? There was an alpha scattering particles, right? I mean, there is a substance that actually release alpha particles. So alpha particles, which are positively charged particles, are bombarded on a gold foil. A gold foil. And the gold foil and all that is actually surrounded by the screen. So whatever will be the result of whatever in the gold foil will be shown here as a bright spot. So what exactly is the situation, right? This experiment is being done by the Ernest Rutherford, and his students are Ginger and Mads. Alpha scattering means the alpha particles are scattered, or you can say bombarded on a gold field. Now, very interestingly, we already know that these alpha particles are positively charged, and when they are bombarded on a gold foil, there are different observations which actually we have observed. Now, what are those observations while the alpha particles are bombarded on a gold foil? Because what the concept was that a simple atom, there is equal number of positive and negative charges, and they are equally scattered. So some of them will be reflected back, and some of them will be experiment result should be as per their journal observation, as per their journal thinking. But the discovery was different. What they have discovered is like that. you can say approximately, let's suppose 1, 2, 3, 4, 5, 6, 7, 8. For example, if 8 alpha particles are being bombarded, what observation we had it is 1, 2, 3, 4, and 5. So 5 upon 8, out of 8, if 5 are going straight down, they will not be deflected anywhere. One of them will be reflected backwards, and 2 will be deflected at certain angles. 5 by 8 multiplied by 100, if you find out, you can check it out. Calculator will tell us very interesting few values. Let's find out what percentage, like give you an idea of that. 5 divided by 8. The value comes to 62. 62% of the alpha particles are going straight. One is coming back. You can say 1 upon 8. So what percentage is just reflecting back? It's only 12.5% will be deflected back, and approximately 24% will be deflecting at a certain angle. Now, these are giving us some results related to how the proton and electrons and everything are being surrounded within the atoms. Now, what are those? The first experiment that in which 62% of the alpha particles are going straight down, it means that most of the alpha particle passes straight through the foil because the atom is mostly empty spaced. Like if you have an atom, mostly it's hollow. The question arises, if mostly hollow, where is the proton and neutrons actually placed? For that one, the second one says some of the alpha particles were deflected as they pass through a foil because they come close to a positively charged nucleus. So what is the nucleus? Nucleus is some mass entity in which you can say proton and neutrons are in which you have proton and neutron. So if they strike there, right? So they are passing forward in a straight line, they deflected at a certain angle. And this one proves that this is a positively charged, a very will have a positively charged element, which is proton, and definitely neutron as well. The next is few are reflected back as well. Why? Because we know that alpha particles being positively charged, when it actually directly comes to this positively charged nucleus, is due to proton. It just reflected backwards. So 1, 2, 3. These three ideas, or these three results, which are being explained in that way, provides us the proper definition for that in an atom, electrons are revolving in the shells, while proton and neutrons are just sitting at the center, and we call that place as a nucleus, right? Now, once you understand that, this is what we call as, these are the results. Now, few things. We represent Z as a proton number. Now, what is proton number? Any element that is a neutral element, protons and electrons are equal. But when you say proton number, we are talking about a mass element. So Z is the number of protons. Here we do call it, but we normally represent it as Z, and this is our proton. And then we have a nucleon number, which is number of protons plus neutrons. This is combined to give you nucleon, which is represented as A. Now, when you represent a single element, you will have a symbol. Along with that, proton number will be written at the bottom, and nucleon number will be written at the top. This is the representation of what we call as nucleoside notation. This is how we represent an atom. This is one of the examples, lithium. It has an atomic number 3, which means that number of protons is equal to 3 and electrons as well as 3. If I say what are the number of neutrons, so mass number, which is 7 in that case, 7 minus 3 gives you 4, which means there are 4 neutrons in it. Okay. So number of neutrons always mass number, or you can say nucleon number minus the proton. Now, there is a small concept here as well, isotope. Now, what are isotopes? We already studied that. Isotopes are the atoms of the same element which are having same number of protons, but different number of neutrons. Or you can say they have same proton number, but different nucleon number due to different number of neutrons. The best example is given here. You can see that this is a hydrogen isotope, right? The first one is hydrogen 1,1, which says 1 proton and 1 nucleon. Nucleon means still number of proton are 1, but there is no nucleon. In the second one, which is deuterium, there is 1 neutron and 1 proton. The next one, there are 2 neutron and 1 proton. So these are the isotopes which are having the same, or what you can say, same proton number, but different number of neutrons in this case. Relative charge. Now, when you say relative charge, remember that generally the charge of so basically, once again, due to some technical reason, we just talked about few things here. If you just say that this is the isotope, you can see yourself, this is hydrogen. Hydrogen got 1 proton here. This got 1 extra neutron and this got 2 extra neutron. And if you see their relative charges, the relative charge of proton is +1, electron got -1, and neutron got 0. So normally we use these relative charges to actually tell their charges. Now here, if you want to find out their relative charges, it has 24 protons, right? So the charge of that chromium is positive 24 for the protons, right? So this is how we actually found out the relative masses, or you can say relative charges of that particular proton in it. So nucleus of a chromium therefore has a relative charge of positive 24, right? So I am hoping that we will continue the same way we are doing it. So hope to see you in the next video in with radioactivity and all that. Okay. And that will be our 23rd video. So thank you very much for watching the video. Bye.